Hello AIND students, I'm Arpan, one of your instructors, and I have here with me Sebastian Thrun, who will be taking some of your questions.
Great, good seeing you again, most of you. Please start.
Sure. Our first question is related to problem solving in puzzles and games. So a student asks, we use problem solving methods such as constraint propagation and search for solving Sudoku puzzles, but these methods do not seem to have any learning in their behavior. Right, so can machine learning be used to solve puzzles and games?
Yes, Atula is the person asking the question, and the answer is yes, in multiple ways. There's two very different ways in which machine learning has been used in the past. Okay, first of all, when you build a game tree, you often can't play all the way to the end. Like in chess, the tree would be so deep that you would spend a lot of time just searching. So typically, you cut off your search at some point. And then you have to assess a value to the current position in a game tree, right? How happy are you, right? So in chess, you'd say, okay, having a queen alive is good, having the queen gone is bad. So some of the value is related to the number of points. But then there's much more complicated elements of that. So what machine learning can do is learn a valuation function, okay? And the valuation function is used to guide the search and also used to cut off and decide when to cut off a search tree. The other way to use machine learning is for controls. When you expand a search node, you often have a choice to do this move or this move or this move or this move. Machine learning has often been used to sort those. And the sorting is actually really important. When you get into real search, alpha beta search, you can find that the order in which you search these nodes have enormous impact on the search complexity. So if you search the best move first, you tend to spend much less time searching than if you search the worst move first.
Right.
So machine learning is often used in search as well.
So I think you know what the next question would be. I'm picking it out of order. How did DeepMind beat the best Go player?
So I'm not part of the DeepMind team, but I know the people really well. And they, in most parts, learned a great valuation function. The problem in Go is that the branching factor is enormous. So you have something like 400 different moves you can make. So if you go 2 plies deep, you have 400 times 400, 16,000. And if you go 3 plies deep, you're basically at a point where your computer just explodes. So that really mandates an extremely selective search approach and a really good assessment of the quality of a board. And where deep learning really shines is in the assessment of the quality of the board. You can look at a board, and even if these patterns are very non-trivial, thanks to millions of training examples, they can assess a really, really good assessment.
Cool. So how would you go about approaching like building an agent for Sudoku or Go, which uses deep learning or machine learning?
I've actually, in my PhD thesis, I wrote something called NeuroChess, which is kind of the deep Go equivalent. It just didn't work out very well. But I've trained a neural network to assess the value of a chessboard. And the mistake that I've made was, the reason why I didn't play well is I started playing on self-play. So you would play and then keep playing its own strategy against itself, and then use the outcome of a game as a training example. Then unfortunately it gave me very few training examples. It took hours and hours for a single game, so I got bored. So I found this chess database of 120,000 expert chess players, and I then just plugged that in. And what the network did very cleverly, I have to admit, and you can look it up in my thesis, it confused causation and correlation. So sometimes there's something indicative of winning. Like, for example, if your queen owns the center of the board, you have a 0.6 chance of winning, turns out. So if you see a grandmaster play and one has the queen in the center and the other one doesn't, has a higher chance of winning. But what's not the case is if you just open up in chess and very quickly move the queen to the center of the board, that you're going to win, because it's a very stupid move. So my network confused what experts do with lots of consideration and tried to rebuild these constellations very quickly and very inefficiently, and as a result lost a lot of games. In fact, I only won 2 games against GNU chess in the day out of thousands that I tried. When you do apply machine learning to gaming, be careful of which way you apply it. I mean, the best way is to self-play. You really kind of train the system. And it goes back to TD Gammon is one of the very early versions of it, neural networks, and most recently AlphaGo, and you can read it up how people did it. Don't just go to a large scale data set and try to fit neural network from there, because you might be surprised how bad the result could be, aka Sebastian's thesis.
That's very interesting. So follow-up to that is, do you have any favorite sort of advanced game playing technique that you would like to recommend to students?
I mean, game playing is hard work, and it's just like a self-driving car. You have to get all the components right. In game playing, there's always components that can be improved. You have to get a really efficient efficient data structures. That's really, really important. And then you have to get your search debugged and your alpha beta search. And if you use killer tables, get all that stuff in order. But then I really believe the big advent now is deep learning, and what's been done there is amazing. And it's not new. I mean, you go back to Jared Tessaro's work in the 1990s on TD Gammon, same stuff. Besides
TD Gammon and maybe the AlphaGo paper, is there any other influential paper on game playing or search that you would like to recommend?
I think there's a long history of efficient brute force searches that goes back to the 1990s in Carnegie Mellon, and then Deep Blue at IBM, which was the Carnegie Mellon team. I don't have a specific reference paper right now that I would say people have to read today, other than getting the core right about alpha beta search and so on.
Okay, that's very good. I'm glad that we're teaching that in our curriculum.
Good.
Yeah.
Good. It's fun to code, actually.
Yes. It's also tricky to understand. I know a lot of our students are struggling with just understanding like the way you assign the different values to alpha beta nodes and how you propagate them.
Yeah. It's good to spend time with it and just draw it out in your brain. It's actually super intuitive, right? You get a bound and say, look, if with this search I can't even get 10 brownie points, then it's not even worth pursuing.
Right.
Or if I find in a branch, or I've already found a really, my opponent already has a really great move in this branch, right? That makes the entire branch not very valuable, no matter what other even better moves you could find by the opponent. So it's really like a very logical thing when you get into it.
Right.
But when you look at the formula, it looks a bit cryptic. So I think spend some time with that.
Yeah. Good. Thank you. So on a slightly different topic, any recommendations for product managers in AI startups and projects? Any additional books or learning materials that might be applicable to them?
I think AI is fundamentally changing in a way. And I just yesterday went to a big AI conference with lots of professors. And I venture to say that the innovation today seems to be largely parallel to the work at universities. There's a lot of people in the academic field that still do inference and representations. And these things might make a lot of sense, but I think the real velocity right now is with all these people doing deep learning and massive data. I think the big shift in thinking is, in the past, when you program a computer, you would meticulously write on every contingency, right? Like 5 million lines of code would be 5 million lines of what can go wrong, right? And now you program a computer by just giving many examples, right? So if you, for example, this week, we are on the cover of Nature, my team in Stanford, we did AI for cancer detection. And all we really did is we tossed a couple of cancerous and non-cancerous images into deep learning, and out came a paper that's now, I think, the 4th best cited Nature paper of all history.
Right.
Kind of crazy, doing deep learning. So what things to study, I guess? I would just approach it with a fresh mind. Take these success examples like AlphaGo. Don't read too many AI textbooks, to be honest. I think it's a mistake to read too much. I think there's too much stuff in there that's historical. And then keep the eye on the prize. Have very clear metrics that you care about. And measure. Like in the Google self-driving car, really saving grace for us was that we had a metric that was the number of miles between what we call critical interventions. And there was a graph every day that we posted, and it, of course, it usually went up, sometimes it went down. And the nice thing about a clear metric is, for one, I mean, you know that you do better and you focus on the right stuff. And secondly, in a startup company, you'll find yourself discussing a lot, right? And the fuzzier the metrics, the more you discuss, right? And the clearer the metrics. In the Google self-driving car team, we never discussed because we had like our top 20 failure things ranked, okay? We had a person ranking it for us, so 73% are this, 12% of this, and then 0.2% of this. And then you sit there and say, oh, 70% of failure is this, let's do that. It really sorts out the procedure at which you approach these things.
That's a very good tip. So set a clear metric, even if it's a simple metric, but as long as it's well defined.
Nice. And as I mentioned, I mean, people often talk about OKRs, and I don't like them because you set yourself a metric and project what the result should be. And I think it's just a big lie. We just don't know. I mean, if you do something interesting new, it's never been done before, how the heck could we know how long it'll take?
Right.
So I love the metric part and say, let's do something that does this. And it might take a day or a week or a year. That's okay. Let's just move as fast as possible.
Okay, that's great. On a different topic, so what do you think about the algebraic topology or geometry-based techniques that are being applied to machine learning for feature discovery?
I have no strong opinion. obviously features is at the core of what happens in machine learning, and there's been many different methods being used for features. Broadly speaking, there are some that are directly derived from the target signal, as is commonly in deep learning, and there's some that derive from other methods, like, for example, maximize entropy in a feature layer that, if you want to say reconstruct the image originally, make sure that the feature layer retains the most information. In all of those, my take is, at this point, is we do a lot in academia, a lot of arguing which one is the better one. Like, is this geometry better or this technique better? Do the vectors have to be orthogonal or not orthogonal, and so on. This has all been killed by the data issue. So you toss in 10 times the data, and the method doesn't matter that much, in my opinion.
Okay, that's an interesting point of view.
It's a new perspective.
Yeah.
When I was a college kid and went to conferences, and a person had a neural network with more than 50 unknown parameters, the statistician would toss them out of the room and say, it's impossible, you can't do this, right? A Gaussian with more than 50 unknowns, forget it. And then I remember there was a guy named Jim Bowen from Caltech. He had 50,000 unknowns in his network, and he couldn't get a paper published because no one believed it's possible. And now we have millions of unknowns. Right. And all the wisdom about bias variance dilemma is been influenced by this, by massive amounts of data. So I think we live in the data age. Spend more time finding good data than arguing what algorithm figures. That's my take.
Yeah, nice. So with all this data, you can also think that the computation part becomes more challenging, and you have to write more efficient algorithms. But at some point, you also have to parallelize and vectorize. So, there were some questions about this. I'm going to read one. Is there an easy way to convert our algorithms to multi-core / cloud-based environments?
This is from Nick Oswald. Hi,
yeah.
Nick. Yes and no. Okay. If you're so fortunate that you can data parallelize, like, for example, you have a neural network and you have 10 million data points, and you put 1 million on each processor, then it's very trivial. Right? If it turns out that this parallelism of data is not good enough for you, and you really have to dive into the mechanisms, as the Google team has done in building TensorFlow, then it becomes very non-trivial. Ever since I was a student, the issue of taking a sequential piece of code and parallelizing it has been fascinating research without a great solution.
Yeah, I think that was touched on by another student who was asking that for a lot of these search and game-playing agents, we've been teaching them fairly sequential algorithms. Yeah. But how do they build up this mindset of, from the beginning, starting to think in parallel?
This is one of the 10,000 or $10 million questions that I've seen hordes of researchers work on, and then not seen a really satisfactory answer, which doesn't mean we're not going to find one tomorrow. In fact, we should find one. The human brain does it beautifully. What I would think is, there's now lots of companies that even build parallel hardware from the get-go, specifically emulating neural networks and similar. Those tend to have difficulty with the connectivity of these units because there's n-square things to pipe around in many cases. I would just recommend every person who's seriously interested, get yourself a machine with 100 cores or 1,000 cores and play with it. My hunch is, in general, as long as you have some specific principles right, like you minimize a metric you care about, aka, for example, gradient descent neural networks, and you have lots of data, most learning algorithms should actually work.
Yeah.
Yeah.
So you think there is a way to break down a problem in such a way that parts are independent and can be solved separately?
Yeah. I wish there was a simple answer. You can't just take a neural network and put it into Amazon Web Services on 10,000 machines and expect a 10,000 speed up, unfortunately. Right. That part, unfortunately, doesn't work. But there are clever tricks to really parallelize the data flow.
All right. Cool. We'll try to explore some of these on the forums with more detailed discussions. Because I feel like this is not something that can be answered in one sentence.
That's no fundamental answer, right? There might be individual situations where, for example, data parallelism is the right thing to do, and it just works.
Cool. Another sort of line of questions is, so a number of these search techniques are, in some sense, like advanced computer science techniques, right? At what point do you draw the line between, okay, this is computer science and this is where we're entering AI?
I always abstain from these turf wars. This is my department or your department.
Yeah.
AI people actually, they used to feel a little bit burned because a lot of stuff was invented by AI people that never was called AI. Time sharing, for example, is an AI result, or certain programming languages came out of AI, and they're called programming languages, not AI. I think, boy, Again, for me, the biggest news in all of computer science is the advent of deep learning. And the reason is it really changes the paradigm how to program computers. I envision a time where computer coding is an unwanted skill because you don't code anymore, right? You just teach. So what we learn today in a nanodegree might actually be useless 20 years from now when we all teach our computers as opposed to code them. And it's going to happen, I'm very convinced. Whether then what computer science is going to do then, I don't know.
Yeah.
The names I don't really care about, honestly.
Yeah.
Obviously, data structures and algorithms is very related to what we're learning in this class here.
Right. Yeah, I think we had a similar discussion on a different forum thread where we're asking students what is intelligence, and where do you start to call something intelligent versus just a smart sort of machine.
Yeah.
Yeah. So I think that
it's in the eye of the observer. I mean, the history is the moment, so you beat the world's best chess player, then chess is not a sign of intelligence anymore.
Yeah.
And that's it.
Yeah.
So intelligence is what it is not.
Right. Yeah, I think David Joyner pointed that out in one of the videos, saying that something is intelligent only up till the point that we don't understand it fully. As soon as we start understanding, it's just a mechanism.
And then there's confusion about, does it have to have a mood, right?
Right.
Or does it have to have emotions to be intelligent, right? And then my example always is I don't want my machines to have emotions. I don't want to come to the kitchen and have the refrigerator being in love with the dishwasher, and therefore dishwasher is not willing to wash my dishes, right?
Yeah.
So I want reliable machines. And then when it comes to this, if you think about civilization in general, about the last 300 years or so, what we've always done, we've always built machines that augment us and make us stronger, right? So there's no humanoid robot has yet farmed a field, but we still have solved the farming problem using massively great machines that still require human intelligence, right?
Right.
So it's always a symbiosis. So for AI, it's the same thing. I think the future, we don't want to build truly intelligent AI. We want to build machines that make us intelligent as people. And that's what's happening.
That's a very good point. Cool. Going back to some of the gaming stuff, there's been some recent interest in poker, right? In fact,
long-term interest.
There has been a long-term interest. There's been some recent news in the world of poker that some of the recent poker agents are starting to beat the best humans. So some of our students were wondering, why is it such a big deal? Why is poker such a big deal?
I think when you look at games historically, starting with checkers by Samuel in the 1940s, working way through Bill, the guy was playing Othello out of Carnegie Mellon, Kai Fu Lee, and then move on to Deep Blue and Deep Thought, Carnegie Mellon and IBM, beating the world's best chess player, to Go, and now to poker. All these, every time a game is taken by computers, there's these smart people who say, but it doesn't do that.
Right.
So when chess was claimed, which was supposedly the hardest game on the planet, it looked simple and silly because it didn't have this enormous branching factor of Go. Now that Go is claimed, Go looks kind of silly, right? It just takes 1 million positions to train from, and you can beat the best. So this was something else. Poker has this element of deceit. There's a human element of deceit that is really essential to the game. And it's not easily mathematically modeled because I can tease you, I can test you, I can learn about you, I can lead you on, right? Therefore, it's another great new challenge. I'm pretty sure once we beat all human poker players with machines, it's going to look silly, and we're going to move on and find something else.
Yeah, but do you think in the process we'll learn something about deceit and,
Oh, you bet. Absolutely, yes. Absolutely, yes.
Cool.
Absolutely, yes. And it's going to be really fun to see when the team comes out. Even in chess, in '97, when Kasparov was beaten, the winning team, IBM team, actually pokered. They changed essential parameters from game to game. And when Kasparov realized, oh, it's playing this way, it all of a sudden played this way. It was making me really upset.
Yeah, I think we saw that in the Go matches as well, where the human player started to understand the patterns and was able to beat the computer for a certain period of time.
Right.
Yeah.
I think the Go folks did not mess with the parameters between different games.
They did
not.
not.
Abstained from it. But I'm pretty sure that the IBM team back in the day did.
Okay. So in general, is there a better is there some canonical technique for dealing with imperfect games and imperfect information games or incomplete information games?
I mean, all of those situations, I don't think there's a generic set of techniques. I mean, there's certainly generic test of techniques if you had game trees, search trees is too long. When you have imperfect information, you can of course integrate it out and go through all possible situations.
Right.
And you die. That's where machine learning comes in. Machine learning has this amazing ability to look at a situation, say this is worth as much, even if information is incomplete, like in poker. And it has this amazing ability to also help you search. So at some point you have to put your foot down and say this is what it's worth.
Yeah. Is there a way to, like, instead of enumerating through all possibilities, is there a way to capture, the possible set of sort of hands, for instance, in poker that someone else might have in a more generic form so that it's, easier to evaluate?
Boy, I have never programmed my own poker agent. I've played it occasionally.
Yeah.
But my suspicion is that, first of all, there's going to be hard rules of stuff that can't be happening. And there's going to be soft rules, like people's behavior reveals some about their hands, obviously. And the more of an account you can get between those relationships, the more informed a guess you might take about what the person's going to do next. But poker is tricky because you can change your strategy, right? You can tease your opponent and then lead them on for a while and maybe train the wrong behavior into a poker algorithm.
All right, we'll keep an eye on how this evolves.
It's a fantastic thing to play with, honestly, and participate in competitions. It's great fun to be in competitions and then talk to other people what they do and learn from them.
Yeah.
It's completely non-trivial, in my opinion.
Yeah, because I think, some of these techniques do extend to the real world where you have, probabilistic scenarios or scenarios where you don't have complete information about the world and you still kind of have to take decisions.
Yeah. I mean, one cynical comment is that I think in the way we make decisions in the real world is unfortunately extremely unrelated to data science and to machine learning and to game playing. It's often extremely ad hoc, right? And it's often based on false facts and deliberately false facts to pursue an agenda. So I think what you learn in a class like this, which is great for a computer, which makes computers in the end superior to us, is not being practiced very well by politicians. Without naming names.
Yes.
But we all know who I'm talking about.
So I think you've mentioned this already several times, but just to confirm, so is ML or deep learning sort of the silver bullet for AI, or is there something else to come that we haven't seen yet?
I think, obviously the game of the week or the year is deep learning and machine learning, as there's no question. And I think it's more than just AI, it's all of society, it's all of computer science. Because it's for the first time we're able to, the way I think about this, we used to do machine learning for a long time. As I mentioned, even my master and PhD thesis was about machine learning. And the kind of brain that we were able to command was like a mosquito brain, okay? And now we are at the point where we have the same methods and we can command a human brain. And of course, a human is much more interesting in making decisions than a mosquito is. That's really, but the algorithms are the same, the neurons are the same, the DNA has a lot of overlap between mosquitoes and humans and so on. So I think we just got the scale right. And what this empowers us to do is to really move away from painstakingly writing code the way we did it in the past, where we like every contingency. We don't raise kids the first 18 years telling them every contingency about life and then say, go run, right? We shouldn't do the same with computers. It's a big mistake, in my opinion. So it's a local minima in the history of computer science. We did this for a while, and we're going to move on. Having said this, there are elements of AI that transcend beyond machine learning, which are really important, and I think we're going to rediscover them. Like, for example, you can't prime an AI system by giving all the books and have information, like, so for example, we want to say, what we just did, diagnosing skin cancer. There's lots of books written about skin cancer where you can really read about it and understand it. And the parsing of natural language is possible, but fusing this back into an image system is not yet done. So all the rule knowledge we have, the written knowledge we have, the language knowledge we have that can contribute is hard to harvest. And equally hard to harvest is this entire notion that you really go to one thing and then you bootstrap to the next thing, right? Transfer learning, as Rich Carano used to call it. When we, for example, look at the Google self-driving car, it's used machine learning massively, but it can't fly a plane, right? And if you were to fly a plane, we would start from scratch. So I think there's a lot of methods that are in the history that will be coming back in. If I were to put my money on one thing, I would be what's called hybrid methods, where you have some rule-based information that you get from somewhere and some data, and you fuse them together.
Cool. I think that's a good note to wrap up on. Do you have any final thoughts for our students? They're in their first couple of weeks in the program, not too long.
First of all, I'm your biggest fan. I'm so glad you guys are doing this. It's a fantastic thing to do in your life, to learn about AI and these skills. And hopefully you spend most of your time doing stuff yourself. I just came back from an international trip and was jet lagged, and I programmed a Sudoku solver, and it was a lot of fun just to program it. It took me about 2 hours and solved even the hardest Sudoku games. Experience this joy and this fun, and be fearless. I think with this, especially this day and age, with the advent of machine learning as a new component in things like game playing, we can fundamentally rewrite almost everything and really have a big impact in the world. I often, when people ask me about the impact of AI, I often tell them, look, 75% of us work in offices in the developed world, whatever that means, like the United States, and pretty much all these people do extremely repetitive work, like your accountant, your lawyer, your dermatologist, right, your judge. They're all doing like legal document discovery. They do spreadsheet math. They do drafting of legal documents. And all these things, in my opinion, AI will just take over. And the reason is, if I watch this long enough, it can do a better and better job. And AI has this advantage that it can learn from many sources and can transfer this knowledge, right? When we humans learn something, it's very hard for us to transfer. Like when we have a new child, they're not born with a high school diploma. But in AI land, if a new self-driving car is born, it has the entire wisdom of all the previous cars. As a result, all these AI systems will get stronger and stronger and eventually be able to do 80% of our work. And when they do 80% of our work, office work, that's going to be really big, right? It's going to be a massive shift in money, in society productivity, and what we do. It's going to be as big as the agricultural revolution. Now it's the AI revolution. So get into this. Find yourself something that you do repetitively, maybe, or your friends do, and put an AI on it and see what happens, and work on this. It's the most rewarding thing. And if you do a good job, come to Silicon Valley and we fund your company.
Yeah, that's awesome. Thank you for joining us, Sebastian.
Totally. It's been a pleasure.
Thanks for joining us today. Hopefully we answered some of your questions. Hopefully Sebastian was able to answer some of your questions well, and we'll probably see you sometime soon.